In this lesson, we're going to cover the Hinge theorem and its converse. This is a supplemental study video, and this is to help you prepare for any quizzes and tests coming up for this particular lesson set. Now, what are our objectives? We want to learn and use the Hinge theorem and its converse. We want to establish and identify true relationships between sides in a triangle and the angles in a triangle. And we want to find the appropriate range of values for an unknown variable. Now, first thing we need to do is to look at what the Hinge theorem is and what its converse is. So, we're going to read the Hinge theorem first. If two sides of one triangle are congruent to two sides of another triangle, and the included angles are not congruent, so one has to be larger than the other, then, this is the conclusion, then the longer third side is across from the larger included angle. So look at the picture under hypothesis with me for 5.6.1. We know that segment AB is the same as segment DE. That's given. We also know that segment AC is congruent to segment DF. That's given. A is an included angle, and it is larger than angle D. That's given. So the Hinge theorem concludes, therefore, that segment BC must be larger or greater than segment EF. Now, a lot of times I get the question, how do I know the difference between the Hinge theorem and the converse theorem? Well, here's a way that you can study to figure out how you know the difference between the two. With the Hinge theorem, you begin with the angles. One is larger than the other, and you conclude the relationships between the sides. So here in 5.6.1, we concluded that BC is larger than EF. BC is not an angle. It's a side. It's a segment. EF is not an angle. It's a side. It's a segment. And we concluded that BC is larger than EF. 5.6.2, the converse of the Hinge theorem. If two sides of one triangle are congruent to two sides of another triangle, and the third sides are not congruent, so one has to be larger than the other, then the larger included angle is across from the longer third side. Okay, look at the picture now under hypothesis for 5.6.2. We know that HJ is congruent to LM. That's given. We know that segment GJ is congruent to segment KM. That's given. We know that segment GH, that's a side, is greater than side KL. That's given. So the converse of the Hinge theorem concludes that the included angle J must be larger than the included angle M because GH is larger than KL. So how do you know that you have the converse? Well, when you have the converse of the Hinge theorem, you begin with the sides and you end up concluding the relationship between the angles. Those are the two ways that you know you're either dealing with the Hinge theorem or the converse. Let's look at the following. Compare the side lengths in triangle PQS and triangle RQS, and then compare angle PQS and RQS. Well, first thing, we know that segment PQ is equal to segment RQ. It's given. They're both 7. We know that QS is also congruent or equal to QS. That's the good old reflexive property. We know that PS, segment PS, is larger than segment RS. That's given. PS is 5.3 and RS is 5.1. Now, what are we going to conclude with? Because now I have to compare angle PQS, follow the letters, PQS, and angle RQS. Which is it? Is this the Hinge theorem or the converse of the Hinge theorem? This is the converse. We conclude that angle PQS is larger or greater than RQS by the converse of the Hinge theorem. Why is it the converse? Because we're concluding about the relationships between the included angles. That's the key. We conclude with the angles in this case. Compare the side lengths in triangle LNK and triangle NML. We know that LM is congruent to KN. They're both 6. We also know that LN is congruent to LN by the reflexive property. I know, therefore, by looking at the angles, that LK, the segment, the side LK, has to be less than the side MN, or we can alternatively write it as segment MN is greater than LK. Both of those statements are the same. I know that this is true by the Hinge theorem. And I know it's the Hinge theorem because I'm given the angles and I conclude about the relationship between the sides, LK and MN. Find the range of values for Z. Okay, first, I know that angle UVT, follow the letters, must be greater than 0. That right there is where you start. You always start by saying either the angle or the side is greater than 0. So that means the expression 6z minus 3 must be greater than 0. Using your algebra, you can conclude that z must be larger than the number 1/2. Now, since side UT is less than WT, that's given, UT is 24, and WT is 25, this immediately means that the expression 6z minus 3 has to be less than the expression 45 degrees. So we take 6z minus 3 less than 45. Add 3 to both sides, and we get 6z is less than 48. Divide by 6, and we end up with z is less than 7. And now we have the range of values for z. Finally, we know that the range of values for z is 1/2 is less than z is less than 7. And as long as z is a number that's between 1/2 and 7, this diagram can work. We can actually draw a diagram like this, as long as z is between those two numbers. The angle of the swings in a circular swing ride changes with the speed of the ride. The diagram shows the position of one swing at 2 different speeds. Which rider is farther from the base of the swing tower? And explain. Now, you got to look at this, and you can probably say, well, duh, it has to be A. And you're right, it is A. But not because we just look at it and say, well, there it is. It's obvious, right? You've got to use reasoning to show why, and because this section is about the Hinge theorem and its converse, you've got to use that form of reasoning. So this is how you're going to show me that you understand the problem. We know that the height of the ride, the tower that is, doesn't change, and we know that the length of the swing does not change. That is, the wire that attaches the ride to the holster of the person. The length of that cord does not change. So as the speed gets quicker, the angle that's formed between the rider and the vertical of the ride grows. It grows. The angle gets larger. So we can conclude by the Hinge theorem that in picture B, the distance from the person to the base is larger because the included angle is larger. Notice we finalized our conclusion with the side of that triangle, from the base of the swing to point to where the rider is on the ride. So as the angle increases, the distance from the base increases. So we know that the person in the picture A is closest to the base of the ride. This is concluded from the Hinge theorem. Again, we're concluding about the sides of the triangles. That's how we know it's the Hinge theorem. Okay, write a 2-column proof. Given that segment KL is congruent to segment NL, we know that those two are congruent. We need to prove that segment KM is indeed larger than segment NM. All right, we begin by saying KL is congruent to NL. That's just given. We know that LM is congruent to LM. That's the good old reflexive property of congruence. LM is a segment that's shared by 2 different triangles. We know that the measure of KLM, now follow the letters because we have to be careful about this. We know that KLM, the angle, the measure of angle KLM is equal to the measure of NLM, follow those letters, plus the measure of KLN. So that right there is the angle addition postulate. This is the crucial part of the whole proof. Look at step 3. If we drop the measure of KLN, if we just drop it and leave it alone, just get rid of it, then the equal sign has to change to a greater than sign. Why? Well, if KLM, let's look at 3 again, if the measure of KLM is equal to the measure of NLM plus the measure of KLN, and I'm assuming that KLN is a positive number. If I just drop KLN, that means that the equal has to turn to a greater than. So the measure of KLM must now be larger than NLM. That's called the comparison property of inequality. Well, if I have angle KLM is larger than angle NLM, I can now conclude that KM is larger than NM. What am I concluding with? Am I concluding with sides or with angles? KM is a side. NM is a side. So we're concluding this proof with the Hinge theorem. When it comes to your quizzes and your tests, make sure you do not come to a conclusion too quickly. Read through the problem first. Use writing to show evidence that you understand the problem and how to solve it. There is no, duh, just look at the picture, it's obvious. You've got to use reasoning to show evidence. You've got to use writing to show evidence. You need to use the names of the theorems and the postulates appropriately to show that. Now, as long as you're doing that, you'll be fine, okay? All right, so throughout this video, I've given a few problems, if you noticed in the lower left-hand corner of each slide, of problems that you can go to that are very similar to the ones given. And so now you'll be held accountable for knowing exactly what I'm looking for when it comes to tests and quizzes on 5.6. God bless you, wherever you are today.